Welcome to the deep dive. Today we're bridging a really interesting gap, the world of quick, subtle electrical signals and the raw power of fluid systems.
Yeah, hydraulics and pneumatics, huge force. We're looking at industrial controls, specifically how you use electricity to tame all that muscle.
Exactly. We're sort of tracking the evolution here. Our source is a technical guide, pretty dense stuff, on system controls. We're moving from simple on-off, sometimes called bang-bang controls,
Right, very abrupt.
to much smarter self-adjusting systems using things like proportional valves and PID loops.
It's really about going from just flipping a switch to actually regulating the power smoothly.
And this matters, right? For anyone listening who works with heavy machinery, knowing how to install, maintain, troubleshoot these electrical controls for fluid power that's critical. It's about safety and, honestly, huge efficiency gains, too.
Okay, so let's kick things off with the basics. How do we actually connect electricity to fluid power? The guide mentions 3 key electrical bits needed. Yeah, basically 3 stages. You've got your input element. That's where the action starts. It could be someone pushing a button or maybe a sensor like a limit switch detecting something.
So it takes that physical thing and turns it into an electrical signal?
Precisely. Then that signal goes to the controller element. Think of this as the brain. It gets the input and decides what to do based on its programming. Used to be complex panels of relays.
Oh, yeah, nightmare to rewire.
Totally. Now it's mostly PLCs, programmable logic controllers. Big advantage there, as the guide points out, as you change the logic with software. No need to physically change the pipes or wiring nearly as much. Super fast, super flexible.
Makes sense. And the third part?
That's the actuating mechanism. This is where the electrical command turns back into physical action in the fluid system. Most often, it's a solenoid-operated directional control valve, or DCV.
Right, the DCV, that's the thing that actually directs the air or the oil.
Yep. It's the gatekeeper. Its job sounds simple. Block flow, allow flow, or change the direction of flow. But how it does that gets interesting.
And they have that naming system you see on schematics, right? The way position thing, like a 42 valve.
Exactly. 42 means 4 ports, 2 positions. Each little box diagram on the schematic shows one of those internal positions, how the fluid paths connect.
Okay. Now, the guide made a really important distinction between air systems, pneumatics, and oil systems, hydraulics. Something about getting rid of the fluid.
Yeah, that's fundamental. Pneumatic systems are open. When the air has done its job, like moving a cylinder, it usually gets vented straight out into the atmosphere through an exhaust port.
I remember reading about quick exhaust valves. They put them right near the cylinder.
They do. It's a clever trick. Lets the air escape really fast when the cylinder retracts, so it doesn't have to travel all the way back through the control valve. Speeds things up a lot.
But hydraulics, you can't just dump oil everywhere.
Definitely not.
Yeah.
Hydraulic systems are closed circuits. The oil has to go somewhere. When a cylinder retracts, that displaced oil has to be routed back to a reservoir tank. It demands careful circuit design and, critically, really clean fluid.
Makes sense. And sometimes, for those really big valves, the electrical solenoid itself isn't strong enough to shift the main part, the spool.
That's right. For heavy-duty valves, you often use what's called a piloted valve. The electrical solenoid is small. It just opens a tiny passage.
Ah, okay.
And that passage lets the system's own fluid pressure, could be air or hydraulic fluid, the pilot pressure, do the heavy lifting and push the main, larger spool across.
So you're using the system's power against itself, in a way?
Kind of, yeah. Control by proxy. Now, inside these valves, the mechanics are different too. Hydraulics often use lapped spools. Incredibly precise fit between the spool and the valve body. We're talking clearances of just a few thousandths of a millimeter.
Wow, tiny. Needs good lubrication, then.
Absolutely. Clean oil is essential.
Yeah.
And they're sensitive. If you over-tighten the housing when you install it, you can actually distort that precise bore and make the spool stick.
Yikes. And pneumatics.
Pneumatics are generally more forgiving. They often use packed bore or packed spool designs. Basically, they rely on O-rings or similar seals. It's more economical, allows for a bit more clearance, and isn't as easily affected by slight imperfections in installation.
So a trade-off. Extreme precision with hydraulics versus ruggedness and economy with pneumatics.
That's the classic trade-off, yes.
Okay, so that's the valve mechanics. But what about control logic before computers took over everything? How did they do and/or decisions just with fluid?
Yeah, the physical logic valves, it mirrors electrical logic. You know how connecting 2 switches in series makes an AD circuit, both have to be on?
Right.
Well, pneumatics has a dual pressure valve. It only lets air through if it gets equal pressure signals at both input ports simultaneously. That's your physical A and D gate.
Clever. And for Aura logic, if either input should trigger the output.
That's the shuttle valve. It's neat.
Yeah.
It automatically senses which of the two input pressures is higher, connects that one to the output, and blocks the lower pressure input. So pressure from either source works. It's a physical OR gate.
Okay, that whole section was about on or off, blocking or allowing flow. Part 2 moves us into, well, shades of gray, right? Continuous control.
Exactly. We're leaving behind the bang-bang world of standard solenoids and getting into proportional valves. This is where things get much more refined.
Proportional means the valve's spool movement directly matches the electrical signal you send it.
Precisely. More voltage or more current means the spool moves further. It's not just open or closed, it can be partially open to any degree.
And because you can position that spool anywhere.
You get amazing control. You can smoothly control the speed of an actuator, manage its acceleration and deceleration, and crucially, you can stop it accurately anywhere mid-stroke. No need for hitting physical end stops if you don't want to.
Okay, so how do we send these shades of gray electrical signals in an industrial setting? The guide mentioned 2 main ways.
Yeah, the 2 dominant standards for analog control signals are the 420 milliamp current loop and the 010 volt voltage signal.
And the 4 to 20 mA loop seems to have a built-in advantage, especially that starting point of 4 milliamps.
It's actually quite brilliant. 4 MA represents the lowest control value, like valve closed or minimum speed, and 20 MA is the maximum. The key is the 4 MA minimum. If the controller ever sees 0 MA.
It knows something's wrong, like a broken wire.
Exactly. 0 MA means fault broken wire, disconnected sensor, something's definitely offline, it's unambiguous.
Which is a big plus compared to the 0 to 10 volt signal, I guess.
Huge plus. With 10 volts, 0 volts could be the minimum setting or it could be a broken wire. You can't easily tell the difference without extra checks. Plus, current loops are generally more resistant to electrical noise over long cable runs, which is common in factories.
Okay, so proportional gives us great control, but then there's another step up. The servo valve. What makes a servo a servo? Aiming for maximum accuracy, right?
Max accuracy, max responsiveness. Servo valves are definitely next level.
Yeah.
Key differences. They usually use a high-precision torque motor instead of a basic solenoid. And crucially, they always have some form of internal mechanical feedback mechanism that constantly checks where the spool actually is.
So it's verifying its own position constantly.
Constantly. That's what gives them such high precision. The downside, they're way more expensive, physically less robust, and extremely sensitive to contamination. Dirt is their enemy.
The guide had a cool example of how that internal feedback works, the jet pipe servo. Sounded intricate.
Oh, it is. It's really clever mechanical engineering. You have a tiny tube, the jet pipe, spraying a stream of high-pressure fluid towards a receiver block that has 2 small openings.
Okay.
If the jet is centered, pressure is equal in both receiver openings. But if the torque motor nudges the jet pipe slightly off-center, more fluid goes into one opening than the other. This pressure difference is what pushes the main spool of the valve.
Right, but where's the feedback?
Here's the genius part. There's a thin feedback wire physically connecting the moving spool back to the jet pipe. As the spool shifts, it literally pulls or pushes the jet pipe back towards the center.
So it rebalances the pressure as soon as the spool gets to the commanded position.
Precisely. It equalizes the pressure in the receiver, which stops the spool from moving any further and holds it steady in that new position. It's a continuous, tiny, mechanical closed loop inside the valve itself. Amazing stuff.
That idea of a continuous self-correcting loop is the perfect lead into part 3. We're moving up to the system level now, process control systems, and everyone's favorite acronym, PID.
Ah, yeah, PID control, the workhorse. So, process control systems are all about automating and regulating industrial processes, keeping things consistent, efficient, reliable. We're talking about controlling variables like temperature, pressure, flow rates, liquid levels, you name it.
And it's a team effort, right? Sensors, controllers, actuators, all working together.
Definitely. You need sensors, thermocouples, flow meters, pressure transducers to measure what's actually happening. You need controllers, typically PLCs again, to do the thinking and calculations. And you need actuators like those proportional valves we discussed, or pumps, heaters, motors to make the physical changes.
And the core strategy here has to be closed-loop control, right? We should probably make that distinction clear again. Open loop versus closed loop.
Yeah, it's crucial. Open loop is like driving blindfolded and hoping you stay on the road. The controller sends a command, say, motor run at 3 RPM, but it never checks if the motor's actually running at 3 RPM. Maybe the load increased and it's only doing 2.5 RPM.
Yeah.
The controller doesn't know, doesn't care.
Right, it just assumes the command worked.
Whereas closed loop is like driving with your eyes open. It uses feedback. A sensor measures the process value. Let's say it measures the motors running at 2.5 RPM.
Then it compares that to the target, the set point, which was 3 RPM.
Exactly.
Right.
That difference between the set point 3 RPM and the process value 2.5 RPM is the error. The controller sees that error and calculates a corrective action, maybe sending more power to the motor to reduce the error and get the speed back up to 3 RPM. That feedback loop is key.
And humans interact with these big systems through HMIs, human-machine interfaces, right?
Yeah.
To see what's going on.
Yeah, HMI is for local visualization and control. And for really large-scale stuff like pipelines or power grids spread over huge areas, you often have SCADA systems, supervisory control, and data acquisition pulling it all together.
Okay, so at the heart of making that closed-loop correction accurate and stable is the PID controller. Proportional, integral, derivative. It all starts with calculating that error signal, set point minus process value.
That error is everything. The PID algorithm uses that error to figure out how much the actuator needs to change.
Let's break down the P, I, and D terms. What does the P proportional do?
P is the immediate reaction force. The bigger the error, the bigger the proportional output. Its job is to make a big, quick correction to get the process value towards the set point fast. It provides the main muscle, you could say.
But it might not get it exactly right. It might leave a small, lingering error.
Often, yes. That's called steady-state error, and that's where ein integral comes in. The integral term looks at the accumulated error over time. Even if the error is small, if it persists, the integral term keeps adding up.
Ah, so it keeps pushing gently until that last little bit of error is gone.
Exactly. Its whole purpose is to eliminate that steady-state error and force the process value to match the set point precisely over time. It ensures accuracy.
Okay, so P gives the initial push, ensures we actually get there. What about D's derivative? Sounds predictive.
It is. The derivative term looks at how fast the error is changing the rate of change, or the slope. It acts like a damper. If the process value is rushing towards the set point very quickly, the derivative term anticipates that it might overshoot.
So it kind of applies the brakes preemptively?
Sort of, yeah. It counteracts the P and I term slightly to slow things down as you approach the target, preventing overshoot and oscillation. It adds stability by looking ahead, predicting where the process is heading based on its current speed.
Let's use that water tank example from the guide. Set point is 1,000 liters. The level drops suddenly to, say, 800 liters. Big error.
Right. So P kicks in hard. The controller signals the inlet valve or pump to open wide, filling the tank rapidly.
Then, as the level gets close, maybe at 995 liters, the error is small, so the P response drops off. But it's still not quite 1,000.
And that's why it takes over. That lingering 5-liter error, accumulated over time by the interval term, keeps adding a little bit of output, nudging the valve open just enough to finally eliminate that gap and reach exactly 1,000 liters.
And all the while, D is watching how fast the level is rising. As it approaches 1,000, especially if it's rising quickly, D applies a bit of a counter signal, telling the valve to start closing before it hits 1,000, preventing it from sloshing over the top.
Precisely. That combination rapid response from P, accuracy from I, and stability from D is what makes PID control so effective and widely used. It's constantly adjusting in real time.
So, thinking back, we've really traced the path of control today from just a simple push-button opening a valve
The basic on-off DCV.
through adding that analog finesse with proportional valves, allowing variable speed and position.
Getting much smoother control.
All the way to this sophisticated self-monitoring, self-correcting PID loop that's constantly watching and adjusting the process.
It really shows how that electrical intelligence, that logic, is what unlocks the precise and powerful capabilities hidden within fluid power. We've moved way beyond just on and off.
Definitely. Now, we did talk about servo valves offering peak accuracy, but the guide threw in a fascinating little caveat near the end. Even with servos, there's still a tiny loss of precision sometimes due to things like the distance the fluid travels and the fact that hydraulic fluid can compress just a little bit.
That's right. The physics of the fluid itself becomes the limiting factor at that extreme level of performance.
So that leaves a really interesting thought for you, the listener, to consider. If we're hitting the limits imposed by the fluid itself, its compressibility, its viscosity, what comes next? What are the future frontiers for controlling fluid power when you need absolute perfection in position or speed? How do engineers need to think differently about the fluid or the system design to overcome those final physical barriers?
Yeah, how do you get even more precise when the medium itself has inherent limitations? Great question.
Something to think about next time you see these systems at work. That wraps up this deep dive.